So today we're going to talk about the different satellites. So far we have been just talking about the major characteristics of data, and also last time we went over some active sensing systems, and today we're just going to talk about all the different sensors that are available and what you can use for doing your project. So lab four for this Wednesday will be your data collection. So far, my plan is to extend the data collection deadline until um, the 24th, the earliest. So, and also, flexible. So if you folks feel like you need more time to think about what data you're going to use, we can also further extend the deadline. So the whole point is, I hope we can get started on, the project as early as possible so that what you're going to do, and then you have your data ready, and you can just collect some reference, maybe just learn things from web resources, or maybe from published articles. So for today, I actually have nearly 40 slides to go over. So what I'm trying to do is, basically I'm trying to go over the major satellite systems that are available. Some are free, but some are not. But I do want to cover because, part of this class is you have to learn the technical perspective, the conceptual perspective, and also you need to know what satellites are available, what data are available, not only for your final project, but maybe for example, maybe for your future job search, maybe you have to learn about all the data. So as we go, I would say think about, keep this question in mind. Think about, first of all, what you can use for your final project. I know some of you do know because you have been doing your research for the grad students, but I think for most of you, it would be just like you're still shopping around and see what can be used. And also just, think about the general data that are available, what you can use for your final project, but also as we introduce a new sensing system, you can also think about, or maybe use the chat, or feel free to unmute yourself. Just chime in if you have a question related to the application of the data, or the possible ways of applying or the different case studies. And I would like to begin with this diagram, and we'll be revisiting this diagram many times for the rest of the semester. So this diagram, which is not very pretty, but it shows you the general remote sensing process from data acquisition to data analysis. So generally speaking, before the midterm exam, we'll be staying at data acquisition. We're kind of like transition to data analysis next week. But after the midterm, we'll be focusing on data analysis, the actual technical component. So far, I think you probably found this ABC, this diagram familiar, because we have been using a similar diagram to show you the energy interaction. That's the foundation of remote sensing, how the data can be used to distinguish between different ground objects. And today we're going to actually focus on the different sensing systems. So we're not really going to talk too much about the difference between satellite high altitude and versus low altitude planes. But in general, we're just going to talk about the sensing systems available. Some are satellites, but some are airborne data. And in terms of the sensing product, in this class, and also in most, nowadays, like modern day remote sensing, we'll be really using digital data, the data you will download from USGS, from ESA, from, any other source to your computer as a file. However, back in the early days, there was still film-based data for different applications, for image interpretation, for photogrammetry, and there are a lot of use of the film-based data as well. However, for this class, we'll be focusing on the electronic-based data, the digital image. And also, actually, in this class, just kind of going back to the the process from data acquisition to data analysis, remote sensing is all about extracting information from data. So right now we're just talking about data, what are available, understanding data. But after the midterm, we'll be introducing more on how to extract information. So, let's still just be patient. I know you folks want to learn more about ERDAs, about running, some processing tools. However, I think really, learning the fundamentals is key, because when you go for a job interview, or when you go for a presentation, you actually will be talking about the different data, the different the fundamentals, and actually your interview questions, if you're searching for something remote sensing related, likely they will just give you basic questions on image data and test your understanding of the fundamentals. So still, there are a lot of reasons why you have to learn the fundamentals. So just get back to Daryl. Sorry, I forgot to post the link, I think. So let me just send you folks the link to the chat now, so that you can all go over things with me. And also I do have a couple links here, so that maybe you can, that'll be easier for you to click on the links. Share real link. Okay, copy. So let me send you the link to the chat here, and I'll be posting the link as we usually do after class. And let me know if this works. And thanks, Daryl, for letting me know. Okay, so back here, in terms of just a little bit more information on the sensing platform and the different possible options. Actually, different sensors, whether they're hyperspectral or multispectral or LiDAR, they do have very specific requirements on the space and stability and in the relative power, so which actually determines the platform. So for example, now if you use a drone to collect data, there are only some smaller lightweight sensors that can be on board of a drone, or depending on which type of drone we're looking at, maybe they're like professional drones that can handle and operate bigger sensors. So in general, this is not really the consideration of our, as geographers or as environmental scientists or earth scientists. But I do just want to mention there are some general requirements by sensor, but also, of course, as technology advances, you'll see more possibilities. Right now people are talking about, and also it's possible to use drone to collect LiDAR data, and especially as LiDAR sensor become more affordable. So in the future, you may be able to collect LiDAR data by just flying a drone, maybe over. But of course, you have to consider the policy and the requirements. So today we're going to focus on satellites, but also some of the sensing systems we're going to talk about today are actually airborne data. So I just want to mention the general idea for today. And for the drones, they have many environmental applications, which is not our primary focus, because we're talking about either commercial sensing system or a publicly available sensing system that you can acquire data that is usually just operating on a daily basis for data collection. So today, like I mentioned earlier, we're going over the satellites, but I also want to just be more specific, and especially today we're going to focus on the satellites operating in the optical spectrum. So which means we're going to focus on the multispectral system, the hyperspectral system, but not too much about the radar and LiDAR, since we already talked about the general idea of radar and LiDAR last time. So let's begin with a video clip regarding a very important data source that you all have heard of, Landsat. So in the last discussion assignment, you folks were reading and basically describing the spatial, the different resolutions of Landsat 8 data. And some of you pointed out there are different generations of Landsat. So let's just begin with this video and just to take a quick look at the history, and also there are actually a lot of images. You can maybe take a look at what this image source can do, because I imagine most of you will be using Landsat for your final project because it's free, it's also long term. Okay, so that was basically a commercial of Landsat, but I think they really deserve the credits because once again, they're free data. So it just seems that whenever I'm on Zoom, Prezi doesn't go very smoothly. So, okay. So the Landsat system has a long history, starting back in the 70s, early 70s, 1972, and it's a collaboration between USGS and NASA. So it's global coverage, which is really a major thing, because even if you're interested in underdeveloped countries where the data are not usually available, Landsat will give you access to historical change analysis. So really think about this. Now you can analyze change about 50 years using the same data, but of course, different generations. We'll talk about the issue with the different generations. So first of all, just a big picture idea. And I believe this is also from the reading, the supplemental reading I posted for today, the different generations of Landsat. So let's take a quick look. Now, first of all, we mentioned they started collecting data back in 1972. So now, right now, the latest generation is Landsat 8. But according to their schedule, later this year, September, we'll have Landsat 9, which is still, with very similar settings as Landsat 8, but they will just give you a longer access to the data. So what I would recommend focusing on here, of course, I don't expect you to remember the dates, like, the generations of their operational date. But the first idea is each satellite, they also have a certain lifespan, because, there's no way a satellite can function like forever. So that is also the reason why they have to keep develop new sensing systems, but also another thing they're trying to do is through each generation, there are also technological advances. to improve their different resolutions, better spatial resolution, better spectral resolution. Actually, you'll see the temporal resolution stays relatively the same over time. The radiometric resolution is another major advance as well. And another thing is, and usually if you focus on a particular period of time, you know, for example, the 80s or the 90s, usually there are two satellites functional during the same period of time. So this is also just to work as a backup, just in case maybe one satellite system somehow malfunctioned, and they just still have to make sure they have consistent data collection available. I guess another thing I would draw your attention to is Landsat 6, and you probably have found out this really short lifespan. So we'll first go over what happened with Landsat 6, and this is something you probably should keep in mind because it's a very special case. So in terms of Landsat, you know, we mentioned there have been 8 different generations of Landsat. However, you know, each satellite, they may have one sensor system, but they also likely have a couple different sensors so that they can collect data to serve different purposes. So in terms of the major sensors, so we'll actually focus on the sensors as opposed to, you know, going through like Landsat 1, 2, 3, 4, 5, 6, 7, 8. So first of all, what happened with Landsat 6 is there has never been Landsat 6 because Landsat 6 failed to reach orbit. And I believe I was reading about it. It was somewhere in the Atlantic Ocean. So there was never Landsat 6, and so that, you know, just to make sure when you search for data, Landsat 6 won't be available. They never collect any data, and you know, that was a failure. So what happened after that is Landsat 4 and 5 had to operate for a longer period of time because they were scheduled to retire. However, due to the failure of Landsat 6, they just have to function for a longer time so that we have consistent data collection. And also in general, take a look at the major sensors. So here I do want to point out the RBV. So RBV is film only. They collect film only data, not electronic. So that is to say we're going to ignore RBV for our discussion today because we focus on digital image analysis, electronic data. So what we're going to focus on is going to be MSS, TM, ATM+, OLI, and TIRS for Landsat 8, as you folks reviewed last time. And also, I think it's, well, basically, there's no ETM because ETM is Landsat 6, and there's only ETM+. We're going to go over, you know, some of the major characteristics of the different sensors. So instead of you know, trying to memorize all the different, you know, resolutions or features, characteristics, I would say let's focus on the relative comparison. You know, I think there was some discussion in the online D2L discussion that some of you were talking about how to combine data from different generations. That was really good because if you're interested in change analysis, especially something more historical from the 70s or 80s, this is an issue you have to deal with. You have to combine data from different generations, and it's tricky actually. But also there are some general solutions which isn't perfect, but it's definitely possible. So that's the whole, you know, the reason why Landsat is getting so popular, even if its resolution is not super high, only 30 meter by 30 meters in most cases. However, the historical, you know, availability is one of the key in global coverage for regional studies. And also in terms of the names, you can basically refer to the different sensors by their short names. For example, you can just say TM, ETM+. However, if you're writing a paper for publication, you do want to spell it out. but in general, you don't have to really memorize, but just to get a sense of the different sensors available. Okay, so first of all, the first generations of sensors, the multispectral scanner MSS, they are on board of Landsat 1 through 5, although 4 and 5 has another more advanced sensor available. So in general, the spatial resolution of the MS sensor is 80 meter by 80 meter. So more specific is 79 by 79 meter spatial resolution. And here I also want to just talk a little bit about the difference between a spatial resolution versus the scene size, the image extent when you collect data. Because I remember some of you were reading about the scene size and maybe you thought it's going to be the spatial resolution, but there are two different things. So the scene size is like when you download data, it's actually the overall spatial extent of the image coverage. That's 185 by 185, or depending on which sensing system you're talking about, but it's roughly the size a square covering a portion of the Earth. For example, like a portion, in the case of Chicago, it covers Chicago, but also it covers majority of the suburbs and a little bit portion of the Lake Michigan. So that's the overall coverage. However, spatial resolution is the cell size, recorded by the sensor. In fact, in the MSS, it has a 6-bit radiometric resolution, and for 1 to 3, it has an 18-day revisit period, the temporal resolution. And you can see for 4 and 5, 16-day, the same as Landsat 8. So in general, the temporal resolution has stayed pretty much the same. And also here I'm attaching the information from USGS. They do talk about, for example, the application of a particular band. However, I do want to point out that when you are performing like a general land cover analysis, or whether it's urban or agriculture or forest, usually you would combine all the different bands. Even though, okay, we see, they're talking about the red band, it's very important for emphasizing cultural features. But even if you're only interested in urban, you still want to have all the other bands available, because they're the additional variables or factors that help you distinguish between different land covers. So, just take a look at the general use, but also keep in mind that usually you do combine multiple bands together. And the reason I'm talking about this is you'll be clear once you get the data. So when you download data from any source, so we will basically use Earth Explorer if you're using a Landsat, you will get one individual file for each band. So which means if you have 11 bands, you will get 11 different files. And then part of the collection and pre-processing is you have to stack the bands together. So basically you will have the option to choose which band I'm going to use. So in most cases, you stack all the bands together, but also there are reasons why you want to throw out some other bands we'll talk about in here. So the next generation of the sensors from Landsat is the TM and ETM Plus. So I'm talking about those together, not because they're very similar, but it's just only because they're comparable in terms of spatial resolution. So you can just take a general look. Both TM and ETM Plus, they have 30-meter spatial resolution for most of the optical portion. However, the thermal band has a coarser resolution. For 4 and 5, they have a 120-meter thermal band, and for 7 ETM Plus, they have a 60-meter thermal band. And one additional thing Landsat 7 provides is the panchromatic band that has a thinner spatial resolution, 15-meter, same as Landsat 8. The temporal resolution stays the same. They all have 8-bit radiometric resolution, which will give you 0 to 256 the different quantification levels. So just a quick review, I guess. Do you folks remember why the panchromatic band has a higher spatial resolution than the other multispectral bands? And also, why is the thermal band has a relatively coarser spatial resolution? Yeah, I guess I'll just,
Can you type that out? Sorry, I'm having trouble hearing. Can you type that in the chat so that I can study it also?
Let me just talk about this. And I'm recording, and Simone, if you have trouble hearing me, maybe you can, come back and just to do the review. So for the panchromatic band, we talked about the trade-off between spatial resolution and spectral resolution. So for panchromatic band, it actually uses the whole portion. If you compare the wavelengths, it uses the whole visible portion, including the near infrared portion. So they're using a broader spectral portion, which gives them enough energy to allow the panchromatic band to collect data at a smaller field of view. So that's why the panchromatic band can give you a better resolution or a higher resolution, smaller. Just only because they're collecting more energy, a broader spectral portion, so that you have the energy to focus on a smaller area. And for thermal, it actually has to do with the discussion we had last week. If you remember the relationship between the amount of power versus wavelengths, and we talked about why microwave sensing system tends to have coarse resolution, because longer wavelengths has actually weaker energy. So in order to collect enough energy, you have to broaden your field of view. And that is also the reason why thermal band, similar to microwave sensing, thermal band has closer resolution. So this is usually the case, although in some cases they may resample the thermal data into the same 30 by 30 meter data. However, the spatial resolution will be a lot coarser. And also here I want to just give you some idea. Whenever I'm doing a general land use and land cover analysis, for example, urban land cover or just general ideas, just classifying forest cover, I would throw out the thermal band for two reasons. First of all, the spatial resolution is coarse. Second, for classifying land use and land cover during daytime, it may be helpful, but in general, I did some research on the spectral signature. I didn't see the contribution of the thermal band. So when I stacked my raw data, I actually only, in the case of Landsat 7, I would go with band 1, 2, 3, 4, 5, and 7. So instead of having all the different bands, I would leave out the thermal for research use, because the coarser resolution and also the temperature probability is only going to introduce some more noise. So that's just my general recommendation. However, I would say it depends on the purpose of your study. If the thermal band does give you additional information, if you, after some research, you found the thermal band does help you distinguish between different features in your study area, and also for the purpose of your analysis, you can bring in the thermal band. And also, I think I only mentioned the idea, the use of panchromatic band, because it has a finer resolution. So there's a technique called pan sharpening. So pan sharpening will allow you to fuse or merge your higher resolution panchromatic band with your coarser resolution multispectral band to generate a higher resolution multispectral image. So, right now you can see after merging the panchromatic band with the multispectral bands, you can generate a relatively better resolution color image. And same color is just what is showing here, but also it may have an additional near infrared band and mid infrared band and far infrared band. And in Ernest Imaging and also some other image processing program, they do offer the tool called pan sharpening for you to merge. So in the case of Landsat 7, you remember the panchromatic band has a resolution, spatial resolution of 15 meter. So that would allow you to generate a multispectral image with 15 meter as opposed to the original 30 meter by 30 meter resolution. So you know that there's some possibility for you to actually improve the spatial resolution based on what is provided by the data. So that's pan sharpening, and also that is usually done, and also you probably have to use the panchromatic band from the same sensor. So which is to say, if you're using Iconis, you will want to use Iconis panchromatic band. So if you're using Landsat 7, you will want to use Landsat 7 panchromatic band, Landsat 8 for Landsat 8. Because you have to make sure they are co-registered and the spatial resolutions are the same. So it really requires high correspondence. Otherwise, it will only just mess things up. And also, you know, so far it seems that Landsat 7 is pretty great. However, I do want to mention another thing that I will really need you to keep in mind. So that is about a malfunction from Landsat 7 that happened after 2003, May the 31st. And it's known as the scan line corrector failure, the SLC failure. So let's zoom in here. So what is basically this failure led to is if you collect data of Landsat 7 after May the 31st, 2003, you'll get an image like this. So what you're seeing, the black lines, they're the gaps. There's no data collected, and which is also, you know, the scan line failure, which is leading to this, you know, linear data loss within your image scene. So, you know, the reason why you want to keep this in mind is because I know many of you might be doing a little bit of historical analysis, because I recall folks were doing change analysis from 2010 to 2019, and then they were thinking maybe I should be using a Landsat 7 because, you know, if you recall, Landsat 8 didn't launch until 2013. So earlier time, it seems that Landsat 7 is a better choice. However, they got the data and found out there are gaps in the image and realized they have to basically redo the data collection again. So keep in mind, if you are using data after 2003, Landsat 7 wouldn't be your option. There's only reason why you want to use Landsat 7 is, you know, this failure actually brought some opportunities for the researchers to study possible ways to fill in the gap. So there are studies about merging multi-temporal data and using some smoothing algorithm to actually fill in the, basically what you're doing is to use additional image and also to use the surrounding pixels to predict the values within each gap. So I think the only reason why you want to have Landsat 7 image after 2003, May 31st, is only just because you want to explore the data correction algorithms, like how to fill in the gap. Otherwise, if you're thinking about just a general like urban growth analysis, water change, or deforestation or agricultural monitoring, for any of those general purpose applications of remote sensing, make sure this data is not going to be very helpful. Landsat 7, you will only want to use Landsat 7 before May 31st, 2003. And this will definitely be on the midterm exam because it's so important. And you do want to keep in mind, because the data are somehow still available, on the portal. So if you download, you wouldn't know until you explore the data more carefully. So keep this in mind, and this will save you time from redoing your work. And now we have Landsat 8, which was launched in February 2013. So this data set, and I do remember, because back then I was approaching to finish my graduate school, and I was like watching the launch live stream. So for Landsat 8, it has a 12-bit radiometric resolution, and also as you folks studied, there are some additional bands. Band 1 for coastal analysis, and they also have a band 9 for cirrus detection. I will have one more slide to show you how the cirrus band looks like. And they now have 2 additional band 10 and band 11 thermal bands. And once again, the spatial resolution is closer because, of the scenario, the rationale we talked about, the longer wavelengths will have weaker energy. So you need a broader view to collect enough data. And panchromatic band, 15 meter, same idea. And this is actually an example from the Landsat 8 cirrus band taken over Paris. So that's the original image. If you're looking at the original image, it looks nice, but really there are not a lot of information possible from this original image, this true color, and that is only because of the cloud covers. And the band 9 from Landsat 8, the cirrus band channel would be able to detect those high altitude and thin layers of cirrus cloud for you to, actually there are some simple algorithm that you can essentially subtract this layer from the original data so that you can produce a cloud-free image. But once again, it's only for cirrus cloud, only those very thin layer, high altitude cloud that can be detected by the cirrus band. However, if you're looking at the tropical region or a lot of regions actually in summertime, likely the cirrus band wouldn't be very helpful because you will have the thick cloud cover, this condensed cloud cover, and which are not going to be removable by regular algorithms. And also, the video clip actually went over some of the general applications of Landsat. Urban growth modeling is one of the major applications. And you can also, get a sense of the spatial resolution. It's not very high compared to the ICONUS data we have been using in the first 2 labs because it's 30 meter by 30 meter by default. So which means everything within, you can imagine everything within a 30 meter by 30 meter would be all averaged out. So if there's a very small house, you won't be able to detect the house, or in some cases there will be a mixture of different net covers, still very hard. So most use of the Landsat data will be regional, metropolitan level, or regional. In the past, we had students. Actually, every single time we had students doing the shrinking of AeroSea, which is a very classic application of Landsat. So that has been a very popular application, and we had folks mapping a flood. Urban growth is also one of the popular applications by the students because you live in the city and you just want to study Chicago. And also, I do recall some people are doing thermal image and just running the temperature analysis and just to see either compare day and night or doing the urban heat island analysis. Possible ways to use, but in general, land use and land power, regional level, you can use Landsat data, and it's free, it's long term. So after Landsat, after the primary system available to us, we're going to introduce a couple more sensing systems. Some are available, some are not very available, but very important to know. So the first one we're going to introduce is actually a European version of Landsat. It's called the Sentinels. So they're operated by the ESA, the European Space Agency. So usually you can consider the system is very similar to Landsat. So we're going to take a look. And also they did a comparison with Landsat 8 just to show you how the spatial and spectral resolution between the two systems are compared to each other. So first of all, I just want to make this clear. So Sentinel-2, only Sentinel-2 is the Landsat-like system, because Sentinel-1 is the radar system. So when you get data, make sure you don't get confused, because Sentinel-1 is LiDAR, is radar. Sentinel-2, 2A and 2B, they're both for the multispectral, the optical image system. And they're running to the A and B, they're pretty much the same. So basically the two satellites are alternating so that they can have frequent coverage of the whole Earth. So they're just really, so depending on where you're looking at the date, you may have A or B, but they're basically identical because they just have this two satellites functioning simultaneously so that you can get better coverage. So just for a comparison between Landsat 7, 8 and Sentinel-2, you can, they actually give you the labeling here, the different portions, and they highlight, I highlighted because the original image wasn't clear. Let me zoom in here. So the best resolution of Sentinel-2 is 10 meter, which is essentially some of their visible portion and also their near infrared portion. They also have a couple 20 meter resolution, and their thermal band is 60 meter, and also including their the shortest wavelength portion. And one thing Sentinel-2 doesn't offer is the thermal band. So they don't give you the thermal band option. So which is to say, if you're interested in doing thermal, you will probably have to do Landsat, because there isn't another better resolution data available. And Sentinel-2 is also pretty recent. So Sentinel-2B was available since 2017, and 2A was only launched back in 2015. So which is also to say, if you're thinking about change analysis before 2015, so far, they're really young in terms of the history. So not available, even if the resolution seems to be more promising than Landsat. So another thing I do want to point out is last year, I had the class did some experiments using Sentinel-2 to classify Chicago. So we're just doing, because it seems to be very comparable to Landsat, but Sentinel-2 wasn't pre-processed nicely as USGS did for Landsat. So what happened was, I'm sure you folks can picture this. So in Chicago, because the downtown area has a lot of tall buildings, and since the data wasn't geospatially, geometrically corrected, so what happens in the downtown region is we see a lot of dark shadow from the buildings. And of course, we have the lake, we have the rivers. So one major confusion was actually from Sentinel-2 was actually from the shadows and the lakes, the water area. So I remember folks were really struggling. So they were just basically making the decision of either classifying the lake as buildings or different ground cover, or they were classifying the shadows as rivers. So either way, it has been a major issue with Sentinel-2. So if you're doing doing work in Chicago or other cities like New York with skyscrapers, I would probably stay away from Sentinel-2 because the data are not geometrically corrected. So which means a lot of pre-processing has to be done before the data can be valuable. But if you are, if you focus on here, they actually break down the near infrared band into many smaller portions. So I would recommend using Sentinel-2 if you're interested in a relatively remote area. or looking at their vegetation covers. I think there are some interesting applications of options for you to explore using Sentinel-2. And of course, it wouldn't be change analysis. And Sentinel-2 is also freely available. And you can download Sentinel-2 directly from Earth Explorer. That's good news. However, if you prefer, you can also go to the ESA's website to download. It's very straightforward. So all you need is to just log in to register for an account, and then you can download their data. So that's about Sentinel-2. And feel free to let me know if any of you has any questions, or because I know we're just only talking about the data. You don't really have the impression of how the data looks like, or you don't get the chance to play around with the data. So feel free to let me know if you have something in mind, but you're not sure. We can try to address the different issues. And also another thing I would like to point out is, because I just remembered another discussion question from you folks' discussion assignments. So I think it was probably Blake and Daryl, because you two were talking about the radiometric resolution, because we know the different generations of Landsat has different radiometric resolution. So we know the pixel values, the brightness values are not directly comparable. For example, the 25 here wouldn't be the 25 in another generation of satellite image. That's a very good point. Of course, direct comparison would be problematic because the same pixel value doesn't mean the same thing. However, I would say, even if you're using data from the same satellite, same sensor, Landsat 8, the 25 in Chicago, like maybe in the summer season versus the 25 in the winter season of Chicago on a basically a different atmospheric conditions, the same 25 will still mean different things. So this is something we'll talk about next week. So that is the reason why you have to perform radiometric correction. Daryl mentioned some algorithms to convert, and also to just basically correct your data. Of course, that's important, but also actually in most cases, instead of using the brightness values directly, the 25 directly, we actually process the data first before we do comparison. For example, if you do temperature change analysis, you would actually derive temperature data first. So you will be applying some equations and algorithms to turn that 25 into a certain temperature value so that you can compare the temperature change. Or if you're interested in, let's say, night level, we'll talk about nighttime imagery later. So if you're interested in night level, light level, not night level, you would convert the data into the illumination values before you compare. And if you're interested in vent power, you will actually classify your data first and to just make them into a categorical vent power map so that each pixel, the 25 now may become water, or it may become vegetation, whatever that is. So you will have several raster maps first before you do your comparison. So what is more common right now, nowadays, especially if you're interested in the application of remote sensing, you would be deriving information first before you do the change detection. So we cover both image classification and change analysis, change detection later this semester. But those were very good questions, and I think it's very important to clarify. We do have, one additional layer of extracting information from the data before we do analysis. So actually, the analysis part is more about GIS, but we focus on extracting information. So that is really, why you have to learn remote sensing within a GIS program, and also why I usually recommend taking a remote sensing class if you're pursuing the GIS, because you do need both. Remote sensing gives you the data, and then GIS will perform the analysis. Otherwise, you're lacking a component of it. So after the Landsat system, there are two broad scale coverage for those of you who are interested in continental and global scale study. I know, this could be of particular interest if you are thinking about analyzing climate change or looking at the broad scale like color change or temperature change or any other change of the phenomena. The broad scale coverage data can be of particular interest. So I'll give you the link here. And also the links are not really the link for you to download. There's a data page where you can read more about each data. So the AVHRR has a spatial resolution of approximately 1 kilometer because it's global coverage. And that's why the spatial resolution is relatively coarse. And they have red band, infrared and thermal bands, and for you to study temperature and cloud cover. And for MODIS, which is actually more commonly used, MODIS data gives you 36 different bands. And it is used for a wide range of applications. And also depending on the wavelengths, the spectral portion, their spatial resolution is also different. Can be as small as 250, but also can be up to 1 kilometer. So for MODIS, actually, if you go to the data portal of USGS, you will see some products derived from MODIS. For example, there are temperature products, and there are vegetation cover, land cover products derived from MODIS. So in general, if global scale analysis is your primary interest, these two data sets should be able to do, depending on what interests you the most, you can choose either one to perform your analysis. And we also have a group of high resolution satellite systems, which we have been using in the lab. They're highly detailed, but let's talk about what they are and what the problem is. So really the problem for the high resolution satellite system is they're commercial, so which means they're not freely available, which is also to say, for research use, they may not be of, they may not be very useful because, to cover a city, you will have a couple scenes, which will cost, a couple $100 to a couple $1,000. But I think it's important to go over the different systems just in case maybe you'll be, exposing to the system or high resolution study for your future projects. So we do want to just quickly go over what they are and the range of resolutions. And the data provider now is merged from their prior vendor called Digital Globe. I'm not sure if some of you are familiar with the name. So it's a US company. So they merged with a Canadian satellite image provider. And now the new name is Maxar. So, but if you search Digital Globe, it will still direct you to the same website, because most people are familiar with Digital Globe. And I actually met someone from Digital Globe 2 years ago. So on his name card is still Digital Globe. I think for American customers, clients, they're still more familiar with Digital Globe as a vendor name. And one of their biggest clients is Google. So which is to say, some of you are already seeing or exploring their data on a daily basis. So for example, the GeoEye and the QuickBird was, their primary data source for Google. In the first one, the Iconos, we have been using in the first several labs. They were launched in 1999 and was the first commercial satellite to collect data at a high resolution. So they have a 0.8 meter panchromatic band, and they have a 3.2 meter multi-spectral band, ranging from blue-green, red to near infrared. And the radiometric resolution is 11-bit, and the temporal resolution change depending on the latitude. And for QuickBird, it was higher, so 0.6 meter panchromatic band and 2.4 meter multispectral band. And you can see how comparable basically the band definition is. So most of the commercial high resolution satellites they just have the visible portion and the near infrared portion, which are actually good enough at a high resolution for you to identify the different objects, like individual buildings or like a block of parks easily from the high spatial resolution. And the GeoEye-1, well, it's another spatial, so you can compare basically as we, as the new sensing systems being launched and developed, you can see the improvement in terms of their spatial resolution. So now the panchromatic band can go down to 0.4 meter. And we also have the world view 1 through 4. So the world view 1 was a single panchromatic band image. So it's very high, but it also doesn't really give you the multispectral information. The world view 2 has a couple more multispectral bands. So the world view systems are actually different because their designs are not only for improving in terms of spatial resolution, they also give you additional information. So this additional spectral bands would allow you to perform a wide range of coastal analysis or studying vegetation. We'll talk about what the red edge is later this semester. So you can really use WorldView 2 with a high spatial resolution to study the detailed spectral information. And then we have WorldView 3, and WorldView 3 was a 0.3 meter spatial resolution, but I do recall when Google reused their data, so they have to resample the data into 0.5 meter resolution for privacy concerns. So there are, this discussion over technological possibilities, but also privacy concerns with really high resolution that everything in your backyard now can be seen clearly from a satellite image. So the revisit time is very frequent, can be done as frequent as less than a day, 24 hours. And actually, many of the uses for the high resolution images are disaster management. So they can really take a frequent shot for within 24 hours before and after wildfire, before and after flooding, just to observe a frequent change over time. And then WorldView 4. WorldView 4 was the same designation as WorldView 3, but was just basically launched for more data availability because the demand was pretty high. And actually here, there's something interesting because we used to offer remote sensing in the fall semester. So I remember in 2016, that fall semester, I had to update the same slide because I had the same slide for many years. I had to update the same slide for 3 times. And the first time was before the semester started, and their scheduled launch date was September. So I first put September something, 2016. And then, actually their launch pad is in California. So the launch was delayed due to a wildfire, unfortunately. So after that, because I think we had this class sometime in October. So back then I had to say, launch schedule delayed, TBA. And then I promised the class to update afterwards. So once we know the exact date, I had to go back and update the final date to be November the 11th, 2016. So like I said, the same idea, very high spatial resolution, 0.3 meter. We can actually take a look, although the data may not be freely available, just to see how detailed the data is.
30 centimeter resolution. That's sharp enough to give city planners, first responders, and military leaders new insights into changes on the surface of the Earth. At Lockheed Martin, we're engineering and building the world's most advanced imaging satellite, Digital Globe's WorldView 4.
We have ignition and we have liftoff.
Launching aboard a United Launch Alliance Atlas V, WorldView 4 will deliver critical information. It will help solve some of the planet's most important challenges. Orbiting at 383 miles above the Earth every 90 minutes, and thanks to a camera so accurate, it can distinguish the make and model of a car. It's almost like taking a selfie from space, but so much more. At Lockheed Martin, we're engineering a better tomorrow.
Okay, so we have really spent some time here to talk about those group of commercial satellites. So let me just give you some idea if you really want to explore the high resolution data. So first of all, they're commercial, so which is to say, if you go to their website, if you search either Digital Globe or Maxar, they will ask you to contact their sales to get, depending on where you're looking at, and they'll just evaluate your needs and just see how much it will cost. However, they do offer some data sample. I found a couple data sample from their website, which again, is not really for actual research use, but it's just more for you to get a sense of how the spatial data high resolution data would look like. And in addition to the free data samples, I actually have a link in the last slide. They also have a open data program that they are publishing data for the major crises, especially just like disaster management services, because we mentioned this frequent high spatial resolution is very valuable for first responders and just to analyze any event. So they do have a long list of open data available for some published this year. Actually, there are a couple COVID-19 related, and mostly are flooding, as I recall from their list. I give you the link on the last slide here. We can take a look if you do want to explore the high resolution satellite image. In hyperspectral, we mentioned those are the sensing systems with more than 100 bands. So we have two major sources here. One is airborne, the AVIRIS, and it has 224 spectral bands, and you can download their data from their data portal. It's not, the coverage is limited, but you can, I think if you click on this link here, it will take you to their, the coverage portal. Like you basically can see where the data are available. And hyperspectral is for those of you who are interested in detecting, basically you have the information on the spectral bands. For example, if you're interested in detecting very detailed vegetation species, tree species, you can explore the use of hyperspectral. And we have another source, the EO1 Hyperion, which also has a similar number of spectral bands. Is spaceborne. It's also a tasking satellite, which means they only collect data per request. And you can get this data from the Earth Explorer. So, this is just a link to show you the information page. So to hyperspectral sensing system, for those of you who are interested in exploring the hyperspectral sensors. And I believe that's my last group to cover today, which is also important and popular. So nighttime imagery, three primary sources. The first two are global coverage of the DMSP OLS versus the Suomi MPP IRS. And we also have one additional source from the International Space Station, and they're actually just photography taken by a Nikon camera, because you can tell from their raw image. Some general ideas on the data. First of all, just a comparison between the DMSP versus the VIIRS. So I'm not sure if you folks can, because I'm only, the screen capture may not really show you the difference very well. But do you folks like see which one sort of has a better radiometric resolution based on the comparison here. It's probably hard to see. Cool. Somehow you're able to tell it's VRIRS. So this second one has a better radiometric resolution because because here I couldn't really zoom in. It's only a screen capture. It does delineate the shape of cities or the patterns better than the older DMSP, which will show a glow of the whole region. So which is to say, in general, if you're thinking about doing a general case of world scale, global scale study, I would recommend going for the VIIRS nighttime imagery for your analysis. And you can compare the radiometric resolution. And also one improvement is the VIIRS, the sensor will have no saturation. So the saturation actually captures the light level. So for the older DMSP, beyond a certain light level, it just all shows as super bright. It doesn't really differentiate between the different levels. However, the DMSP has a longer history. So they do have a digital archive available since the 90s, and the VIIRS is pretty recent from 2011. And spatial resolution is comparable, but in general, VIIRS has a relatively high and stable resolution. So the VIIRS is considered as a major improvement in terms of the nighttime image. For the ISS photos, International Space Station, they're actually just taken by the astronauts on board of the ISS using a Nikon camera. I have used the ISS photos for research. It was tricky because usually some are blurry, because it depends on really how the image was taken, and most of the image would come at a perspective, which makes the geometric correction very hard. So this one is probably the best I can get for Chicago. That is relatively in a right perspective that doesn't take much distortion if I do the geometric correction. So the resolution also depends. In some cases in Chicago, I found a couple that had 20-meter resolution. So they promise, some cases you can get 1 meter resolution, but also in some other cases they only have 1 meter. And since they are only taken by hand, most of the images are on like mostly cities, urban area, or interesting area. So there's not like a systematic data collection process. And also speaking of the International Station, International Space Station, I do want to just introduce something exciting that is going to be available that you can search for GEDI, which stands for Global Ecosystem Dynamics Investigation. So this is an ongoing global LiDAR project that is going to be collected from the International Space Station. It's ongoing, so hopefully maybe sometime next year we'll have data available from this system that we can use, GEDI. Just also another source from the International Space Station. And finally, just a couple links to getting folks started. The Earth Explorer is where we can get Landsat, Sentinel-2, and the global coverage data from NASA and NOAA, the different public sources. And if you're interested in the high spatial resolution data, that would be the Maxar. They have the first link is their data samples, and the second link is their open data for disaster management. And for those of you who are interested in doing more LiDAR, we have open topography. We also have the national map for areas within the United States. Okay, so I think that's the major things I would like to cover. And also, just reviewing the final project option, I think all of you have done your choice here. So we have 3 people are going to planning to work in a group, which I'm not sure if you, because I remember seeing the spreadsheet on that we shared last time. Let me share it with you again. So right now I'm only seeing Simone and Rob, the 2 names there. So I haven't really seen other people, put down your name. So not sure if you have already found out who you want to work with. But I'm going to share the link once again, so that maybe we can still use the spreadsheet to figure something out. Yeah, I mean, it's really tricky now to try to find someone to work as a group. So, if you have a topic, maybe you can start with a topic. But also, if you wouldn't mind, I just want to work with someone, and so that you get another person to collaborate, and also to maybe get some verification. So I think that could be helpful. So Wednesday, Lab 3 is the Wednesday, the LiDAR data one. We also have the second review assignment, which is only a write-up. So you can turn in your write-up through D2L. And Lab 4 is project data collection. Right now, I'm putting extending the due date to be the 24th. So that is, I think, 2 weeks from this Wednesday, right? And also that is the midterm work day, I think. Midterm is going to be take home. But I'm also willing to extend the deadline furthermore if you want to have some longer time to to think about your options and maybe just evaluate a few different sources or maybe do some research. Yeah, that's actually all we have. Yeah, Daryl just put on a new project on LiDAR data. Yeah, I think LiDAR data could be very doable too, as you folks see, the data extraction, doing vegetation, we do have data available, and also it's getting really popular now. So, although with LiDAR, you wouldn't be really doing too much exploration of land sites, but it can be a very helpful exercise too. Yeah, let me see. So for Lab 4, so what I'm going to do is at the beginning of class on Wednesday, I will give you folks a demo, which I will also record to show you how to use Earth Explorer to get the different data. And also I'll be sharing with you a couple other videos on how to stack data, because for the Lab 4, I will require you to do more than just download the data to your drive. You will have to put the data together and also to subtype your data. So I'll share with you videos, and also I'll give you a demo. So there will be a couple video instructions this time. So yeah, I think that's all for today. Let's just think about the group project options, the final project options. And Wednesday we can also just set up some breakout rooms if you folks want to maybe check in with each other and to figure things out better in by talking to someone, as opposed to just only like using the spreadsheet without seeing others' faces. Okay, so that's all I have today. I'll see you folks on Wednesday, and I will definitely hosting my office hours now if you want to stay and have any questions.
Thank you, Professor.
Sure.